Okay, so when we're talking about NMR, if I was smart, I would have included this in the lecture. The very first slide we had in the class was basically a slide of the electromagnetic spectrum, and infrared came in the area of bond vibrations and bond bending. Nuclear magnetic resonance comes in the region basically of radio waves. So they are very low energy, and this is associated essentially with changing the spin of nuclei. So we're not even talking about bond energies for bonds moving or bending or anything like that, but it's just changing the spin of an atomic nuclei. So it's very low energy. So many nuclei have a property which we call spin, and these nuclei behave as though they are little spinning tops. And so the nuclei in question, which we're looking at, will either have an odd mass or an odd atomic number. And when they have this, it is quantized in a spin angular momentum and a magnetic moment. So the nuclei which we're interested in are all going to follow these two characteristics. They're either going to have an odd mass or an odd atomic number. So they're going to have this magnetic moment. And so any nuclei with spin is allowed to have a certain number of spin states. And so these spin states, first thing is they're quantized, so they're discrete. And it's determined by their nuclear spin quantum number, this letter I. And so basically this is a physical constant for each nuclei. And the number of spin states is 2I plus 1. So this is going to appear as a series from minus I to plus I. So if you've got a proton, its nuclear spin quantum number is 1/2. And so the two spin states for hydrogen are going to be, let's draw this, minus 1/2 and plus 1/2. For deuterium, so it's got an I of 1. So 2 times 1 plus 1 is going to equal 3. So it's going to have 3 spin states, whereas hydrogen, like the proton, 2 times 1/2 plus 1 is 2 times 1/2 is 1 plus 1 equals 2. So it's only got 2 spin states, minus 1/2 and plus 1/2, whereas deuterium is going to have 3 spin states. It's going to be minus 1, 0, 1. The most abundant, so the most interesting, if from an organic chemistry perspective, carbon, because organic chemistry is all about carbon. Carbon's atomic number is 6, right? And so carbon 12, the most abundant of all of the isotopes, is also even. So there's great big 0. There's no, you can't run a proton, an NMR on carbon 12. So this is kind of unfortunate. So we are sad that we don't have this sort of type of spectroscopy for the most abundant atom that we're interested in. But the good news is carbon 13 is NMR active. That's another way of saying this. And it's got an I of 1/2. So there's 2 spin states here. Again, that'll be minus 1/2 and plus 1/2. Most of the other elements are, nitrogen's a mess, unless you're an organic chemist. We'll see later on why nitrogen's a bit problematic, so let's cross that one off. Oxygen, again, this is not NMR active. Fluorine F19 is, and so is phosphorus. And these are both interesting. These can be really useful. Fluorine's used in medicinal chemistry all the time, and it's got a really nice little beautiful spectra. Nice thing is fluorine 19 is like basically 100% abundant, so it's nuclear, so its natural abundance is really high. So fluorine can be used much like proton. So the trouble with carbon-13 is that its natural abundance is approximately, I think it's 1.9%. It's really low. So this means that you need to do lots of scans with carbon. And phosphorus, of course, is really important in biochemistry. So that makes that a useful nuclei to look at. So that's basically the starting point. Let's erase all of this stuff. Oh, I must be drawing on PowerPoint. All right. Let's move on then. There we go. All right, I'm not drawing on PowerPoint. Thank the Lord. Okay, so in the absence of a magnetic field, basically the spin states of all these nuclei are degenerate. So that means they're just, it's just random. There's no, the energy level's the same. There's no alignment to this. But once you put them in an applied field, it's funny that the Earth does have a magnetic field. I guess it's not strong enough to align the nuclei in a useful manner. But once you put it in a strong applied field, the spin states no longer are equivalent. So the key point is that these little nuclei we've got, they are spinning and they're charged. So each one of these nuclei basically generates its own little mini magnetic field. And so when you put it in a large magnetic field, the nuclei can either do one of two things. The field that they're generating themselves, because remember there's in physics there'd be all these the right-hand rule and all this sort of stuff. The nuclei can either, if this little big arrow here is basically meant to signify the direction of the applied field, applied magnetic field, the nuclei can either align with it, so it's pointing up, so its field is aligned with it, or it can be opposed to it. So we would call this, in layman's terms, spin up or spin down. So they can either be aligned or opposed. So normally the energies are degenerate. There's no alignment, so to speak. But when you put it in a strong applied field, those spins which are randomly aligned are either going to align with the field or they're going to align opposed to the field. So that's what's going to take place. So this experiment is going to be done in a big giant magnet. That's the key point. So this experiment is done in a magnet, or this technique is run in a magnet. And so in hospitals, nuclear magnetic resonance, NMR, it's the exact same principle for NMR in an MRI machine. And so magnetic resonance imaging is what we're looking for in the hospital setting. And in the hospital, what they're looking at is basically the water density in the various tissues and that sort of stuff. And of course, water's got protons on it. So this is how this is all working. I guess when they were developing this technique for hospitals, patients didn't like being put into machines which had the term nuclear associated with it. So they basically changed the name so it's magnetic. It doesn't even have nuclear in it. That's an interesting little tidbit there. Okay, let's clear all these drawings. Okay, so, right, next slide. So, what's going on here is that this is what this is supposed to show. Over here, these two energies are basically the same. They're degenerate. There's no field. Then when you put it in an applied field, you can either be opposed to the field and be higher in energy, or you can be aligned with the field. So you can be the spin up or you can be spin down. And the way that this technique works is now we've got a, there is an energy difference between these two spin states. And of course, E equals Planck's constant times some frequency, right? So what we are going to do is the nuclei which are in one spin state, we are going to hit this with just enough energy which matches this difference, and we are going to promote that nuclei to the other spin state. And from there, it's going to basically relax back down to its original spin state and give off some energy, and you can detect that. So that's basically the way that this technique is going to work. So yeah, they've sort of reversed the way, yeah, so this is basically what it's going to work. So this energy, this gap is quantized, and only certain frequencies of energy will match it. You're going to change the spin state of one, promote it, and then as this relaxes back, you can actually detect this energy. You can, so I believe with the earlier machines, you would detect the energy going in, and later on with the new machines, they detect the energy going out. So there's two ways you can get this technique to work. Does that make sense so far? I will take that as a, since I don't have the little video on, I'll take that as a yes. All right. Right. Okay, so now the next point is, as our technology gets better and as our magnet strength gets better, lots of good things can happen. Okay, so what this diagram here is showing is that, so this is the degenerate state here where these two levels are supposed to be the same. And as you travel along the x-axis here, the field strength of the magnet itself is increasing. So so here we could have a magnet of certain strength, and the two energy levels would be here and here. But if you increase the magnetic field strength, then the energies are now here and here, and the energy difference between the two spin states is larger. So that's basically what this little diagram is trying to depict. So as you increase the field strength, the energy level difference will increase. There's a second factor which also is very influences the NMR and the technique it is, in a similar way to this field strength, and that's about the nuclei itself. So the nuclei, so some of the NMR active nuclei was like H1, carbon 13, fluorine, what was another one? Deuterium, phosphorus 31. all of these NMR active nuclei have a different ratio of magnetic moment to angular momentum. And this is commonly called the magnetogyric ratio. And so this is just basically a constant that each nuclei has. And depending upon this constant, this will influence where on the chart this happens to be. So if this, like for example, hydrogens is approximately 300 and carbons is approximately, I think it's 75. I think on the next slide we'll actually show it. So this means that like carbon is basically 1/4 that of hydrogen. So if hydrogen in a magnetic field of, magnetic fields are usually measured in megahertz. So if carbon is in a 300 megahertz magnet, sorry, if hydrogen is in a 300 megahertz magnet, it would be, the energy might be here, the energy difference. But carbon in that same 300 megahertz magnet, because it's only 1/4, this ratio is only 1/4 of that, carbon's is way down here. This is where carbon-13 would be. So this energy difference would be a lot smaller. And it's going to influence the way the spectra looks. So that's just another little thing. And I think the next slide basically is talking about this. So yeah, I rounded up a bit. So hydrogen is 2.67 and carbon is around 67. So this is still roughly approximately 1/4. So that means that carbon, we're going to need to do quite a bit of work with it to get its to get a good spectrum out of it. Whereas if you look at fluorine, fluorine's ratio is almost exactly the same as hydrogen. So a fluorine NMR and a hydrogen NMR are going to be very similar, whereas a carbon's is, because this ratio is way lower, it's going to be different. And phosphorus is somewhere in between. The other thing which is interesting is that you notice that fluorine, phosphorus, and hydrogen, the natural abundance of these isotopes is super high. And poor little old carbon here, I was wrong, it's not 1.9, it's 1.1. So it's a lot lower. I think, yeah, before we get into all of the rest of it, this is, we'll probably stop here. Like the physicists, like, so this is basically the field strength here. This is what that means. And they're comparing apples to apples here by putting these all at 1 or 1.4. So what we'll do on Thursday is, actually I'll probably put together some little questions in Top Hat and we'll do a little bit of question and answer session at the start. And then we'll go into, we'll go through the process of how resonance works and what we're looking for. And then we'll show you, we'll look at some spectra and that sort of fun stuff. Yeah. So what we're going to see is that the electron density around the atoms themselves is going to play an influential role in where each nuclei is going to resonate and be detected. So that's basically we're going to see. So protons that have got lots of electron density around them are going to be, it's going to take more energy to get them to resonate. And protons that are stripped of electron density are going to resonate at lower frequencies. So, and then that's where on the chart, we're going to be able to see where any given proton will resonate. And this is a way of, and so yeah, we'll be able to look at a chart and be able to figure out, oh, is this an aromatic? Is this a double bond? Is this an aldehyde? That type of stuff. So that's basically where we're going to go with this. Alrighty. Yes.
I have a question. Like, it's not related to this, but the recordings for mass spec, are you gonna post it on Top Hat, if anywhere?
Oh yeah, I did. I think I recorded that last week. So yeah, I'll do that.
Oh, okay. Okay, thanks.
Yeah, I haven't done that yet, have I? No, I'm sort of behind on my posting of recordings, but yeah, I'll do that.
Thank you.
Anything else? Okay. Well, I will see everybody on Thursday at the latest.
Great. Have a good day, Dr. Hill.
You too.